In 1924, French physicist Louis de Broglie proposed that the physical matter making up our universe inherently exhibits wave-like behavior. He defined a simple mathematical relationship. The physical momentum of any particle dictates its quantum wavelength. This diagram illustrates how de Broglie's math successfully models an electron bound to an atomic nucleus. Notice the exact integer wavelengths. The standing waves labeled n equals 3 and n equals 4 perfectly map to the stable, discrete orbital paths predicted by the Bohr model. This framework functions flawlessly when dealing with a confined space. It resolves the mechanics of particles trapped in a localized potential well. But extracting an electron from the atom introduces a specific mechanical conflict. Attempting to apply this same single-wave logic to a free-moving particle produces a result that defies classical kinematics. We shift our scope from the tightly bound atomic nucleus to a single, free material particle, like an electron moving linearly through empty space. To represent the classic textbook assumption of a de Broglie wave, we superimpose a standard, monochromatic sine wave over the moving particle. To understand the physical mechanics of this wave over time, we calculate its propagation speed. In wave mechanics, this is called phase velocity, the specific rate at which a single crest, or plane of constant phase, moves forward through space. Common intuition assumes the phase velocity of this wave and the physical velocity of the material particle are identical. They appear to travel as a single unit. Yet calculating this phase velocity using standard quantum relations yields a result that clashes with the established speed limit of the universe. This slide shows the classical wave mechanics formula. Phase velocity is calculated by dividing angular frequency by wave number. To apply this classical wave equation to a physical particle, we have to integrate Einstein's relativistic principles for energy and momentum. By substituting relativistic energy and momentum into the fundamental quantum relations for frequency and wave number, the classical equation transforms. We are left with a final, derived equation. Phase velocity equals the speed of light squared, divided by the physical velocity of the particle, u. This text asks us to look at the denominator of this new equation, representing the particle's actual physical velocity. Because electrons and protons possess physical mass, Einstein's special relativity dictates they can never reach the speed of light. So we are taking the speed of light squared, a massive constant, and dividing it by a sublight number. This document highlights the result of that operation. The resulting value for the wave's velocity is strictly greater than the speed of light. The derivation results in a matter wave that travels faster than light. By this logic, a single monochromatic wave cannot represent a moving particle without violating the principles of special relativity. We must ask what this mathematical contradiction actually looks like in physical space over time. This diagram illustrates a material particle and its theoretical wave starting from the exact same position. As established, the physical mass of the material particle restricts it to traveling slower than light. But as the phase velocity takes over, the wave accelerates past the c boundary. The consequence is visible on the right. The wave physically detaches from and entirely outruns the material object it is supposed to define. Because this wave dictates quantum probability, the particle's probability of existing is now sprinting away from its actual physical mass. To fix this failure of logic, physicists had to abandon the idea of particles as single, simple waves. They cannot travel together. Austrian physicist Erwin Schrödinger recognized that a localized particle must instead be built from a composite of waves. This text outlines his required mathematical substitute for the single wave, the concept of a wave packet. We can begin constructing this packet by layering two distinct sine waves, each with slightly different wavelengths and frequencies. Adding an entire distribution of multiple waves to the stack simulates a continuous spectrum. When we sum these distinct frequencies together, their overlapping geometry reveals a combined interference pattern. At the outer edges of the pattern, destructive interference causes the wave amplitudes to cancel out entirely to zero. In the center region, constructive interference creates a strong, localized peak. This localized probability envelope is the quantum wave packet, the mathematical framework used to define a particle in motion. Setting this newly engineered wave packet in motion allows us to observe its kinematic properties. Direct your attention to the individual ripples pulsing rapidly on the inside of the packet. These internal ripples still travel at the impossible phase velocity, faster than light, but they are strictly confined inside the envelope. The physical resolution lies in the motion of the outer boundary, the envelope itself. The specific speed at which this overall probability envelope travels through space is known as group velocity. The exact center of this traveling envelope identifies the highest localized probability of finding the physical mass. Because of the interference pattern we built, the mathematical group velocity of this packet equals exactly u, the physical sublight speed of the particle. We now have a consistent dynamic cycle. Internal phase waves race forward, vanish at the front boundary, and reform at the back, all while the primary envelope moves steadily with the physical mass. By engineering the wave packet and cleanly separating phase velocity from group velocity, early physicists successfully anchored the abstract quantum wave to physical reality, preserving the laws of relativity.